Hi everyone, welcome to Group 8's presentation on the non-electric centrifuge for remote and rural Amazonian communities.
Hello everyone and welcome. I'd like to introduce our team, Centrifuge. I'm Rebecca Goodrum and I am in my third year of biomedical engineering.
My name is Tiana Bresson and I'm in my third year of biomedical engineering.
My name is Gwyneth Earhart and I'm in my third year of mechanical engineering.
Hi, I'm Emily Morin-Berge and I'm in biomedical engineering.
My name is Logan Arnold and I'm in my third year of biomedical engineering. The agenda for today's presentation on the non-electric centrifuge will begin with the problem, the scope, the constraints, the criteria, and then it'll go into the design process, the design solution, as well as the design defense, and it'll end with conclusion and recommendations.
So just kind of looking at the problem that we're trying to solve, our focus is on the Loreto region, which is part of the Peruvian Amazon. And we're really looking at anemia prevalence and the severity of anemia and how we can diagnose it without using electricity and for these really remote indigenous communities. Looking at that map, that's the severity of anemia. Anemia affects about 30% of the population. And if you look specifically in Peru where the arrow is pointing in that top region, anemia is very prevalent in the Amazon. And so the problem here is the lack of resources and lack of technology education and really this access to healthcare. And so our solution specifically for anemia was to improve how they diagnose anemia with the non-electric centrifuge. So just kind of breaking down how to diagnose anemia and how centrifuging works. So anemia is characterized by the volume of blood or the percentage of blood that red blood cells take up. So when you have that 100 milliliter tube, basically you can look at just eyeballing it, that 40%, 50%, how much hematocrit or volume of red blood that takes up. And so it'll sediment based on density. So red blood cells being the most dense at the bottom, white blood cells with platelets, and then plasma. And we're really focusing on the red blood cells. In terms of RPM and RCF, we're going to get into that throughout the presentation, just how fast you need to spin and at what diameter to really make sure it sediments properly. And then also in terms of storage, what's great is that once you have those blood samples, if you centrifuge immediately and diagnose immediately, you don't actually have to worry about cooling anything.
Our objective was to aid in providing medical support to low-resource remote communities by designing an affordable and reliable non-electric centrifuge. The scope of our project included the RPM, the time of centrifugation, the complexity of use, the material, the cost, the ease of maintenance, and of course industry standards and regulations. The capillary tubes, collection and storage of blood, disease diagnosis, training, implementation, manufacturing, distribution, sanitization, lab practice, and the creation of a physical prototype were outside of our scope.
This design must be able to go a minimum RPM of 400 for 5 minutes, as this is the minimum force required to separate red blood cells. It must also be able to centrifuge 50,000 cells per milliliter density of blood to follow standards. To be able to be used in the rural communities of Peru, the centrifuge must require no electrical energy source. And finally, to follow regulations, the final design must comply with the Canadian FDA guidelines for medical devices. To help guide the design, a list of criteria was made. This included minimizing both cost and the weight and bulkiness to allow it to be financially acceptable and easily transportable within these communities. It should be easy to use with minimum human energy required so that health workers with little education can use it without easily tiring. For simpler repairs, the use of standardized parts should also be maximized. And as well, this device should be durable and long-lasting whilst remaining consistent and reliable with their results.
Our design process very closely followed that of which was outlined throughout the course. Once our problem was defined, an in-depth literary review was conducted. This was performed with the goal of focusing the scope of our project and guiding idea generation. Research was conducted on the types of centrifugation in tubes, namely micro and macro centrifugation, the composition of a centrifuge, such as the casing, the axle, the rotor, the gear systems, and the buckets, both fixed, angle, and swing, the requirements for proper blood centrifuging, and finally a market analysis, which showed very limited non-electrical designs. From this research, 5 alternate solutions were generated. These designs took inspiration from various existing designs such as a mop bucket, a salad spinner, a wind-up toy, a bike, and a hand crank. Our final design was chosen using a weighted decision matrix. Various tools were then used to create a virtual model to optimize and validate the final design.
To validate our design, multiple tools were utilized. Hand sketches were first drawn to help visualize our 5 possible designs and describe advantages and disadvantages of each. A decision matrix was then used to rank our designs and determine which one would be the best option. This was also confirmed using a sensitivity analysis. The preliminary design was then modeled using SolidWorks with the selected materials to ensure it met the constraints and the criteria. And using ANSYS, this model was tested for failure to ensure it could withstand the necessary conditions it would undergo.
To begin discussing the design solution, I will do an overview of the components that make up the non-electric centrifuge. The design solution of the non-electric centrifuge can be seen broken down into its main components via the exploded view located on the left-hand side of this slide. The cooler body and lid act as the exterior of the centrifuge. The foot pedal and pedal base fit into the cut made into the cooler body, and the gear mechanisms and rotor are located within the cooler body. As seen on the right-hand side of this slide, an animation of the assembly exploding and collapsing can be seen and visually depict the general overview of the design solution and how everything fits together. This animation shows all sides and angles of the design solution and specific components and mechanisms, which will be further discussed later on within this presentation.
So now I'm actually going to talk about how our centrifuge works. As the user steps on the pedal, the geared teeth on the pedal at one end will mesh with the large gear, making the large gear rotate clockwise. The small gear, which meshes with the opposite side of the large gear, will rotate counterclockwise. Inside of the small gear is a one-way clutch bearing, where the axle will slide into. The other side of the axle is press-fitted into the rotor so that the axle and the rotor spin as one unit. The base is used to hold all of the mechanism parts together, including the two rods that are designed to fit tightly inside the holes on the base, while the pedal and the large gear are able to freely spin along the rods. There is a torsional spring that fits along the longer rod and has one end secured to the base, while the other end is secured to the foot pedal. Two important components of our design are the torsional spring and the clutch bearing. This spring provides resistance as the user is pushing down on the pedal, and it makes sure that the pedal will always return to its most upright position. As the pedal is being pushed down, the bearing rollers aren't able to freely spin, meaning that the axle can be driven by the small gear. But as the pedal is moving back up, the gear is actually rotating in the opposite direction. In this direction, the bearing rollers are actually able to freely spin, allowing the axle to continue rotating counterclockwise, even when the small gear isn't. If the design didn't have this type of bearing, the rotor would actually spin back and forth rather than in a continuous direction, and it wouldn't separate the blood properly.
In determining the best solution, materials are crucial. An important aspect of our design is that it should be lightweight and easily transportable whilst remaining durable. It is for this reason that we chose to model our design largely out of plastics. For the cooler itself, high-density polyethylene was chosen as it is strong, lightweight, and weatherproof. It has a long service life of up to 50 years and can then be further recycled at least 10 times after use. A long-lasting gear needs to be tough and rigid, with low friction and good wear properties. For this, we decided to choose acetyl copolymer for the gears and the connecting pedal. This material maintains all the necessary properties whilst being lightweight and long-lasting in hot, dry, and wet environments, which is ideal for its use in Peru. Polypropylene has been used for centrifuge rotors before and has been found to work better than metals due to its resistance to fatigue and stress, making it ideal for our centrifuge also. It is lightweight and will require less energy to spin, meeting the criteria of this design. The axle must be strong enough to withstand the weight of the rotor and the applied moment. We selected plain carbon steel as it has high strength and toughness and is often used for axles. These materials are all easily processed whilst remaining inexpensive. For the raw materials alone, it is estimated to cost only $20 per centrifuge, which will allow our design to remain cheaper as per the criteria.
When discussing the design defense, it is important to investigate engineering principles and theories to determine if a design is feasible and if it will perform the desired function accurately. For this design defense, gear theory was used for determining the required pitch diameters, diametral pitch, and gear meshing when using a bevel gear system. The diametral pitch must be the same for the gears coming into contact with one another and is determined by dividing the pitch diameter by the number of teeth for a specific gear. On the right-hand side of the slide, the main components of the gear mechanism are labeled within the schematic. So the foot pedal, large gear side 1, large gear side 2, and the small gear are labeled within the picture. For functionality, gear theory aided in finding a gear system that would work for this design solution. Animations of the gear system, with and without the foot pedal driving the motion, can be seen on the left-hand side of the slide. A part of the defense also includes human fatigue, which is important when considering the input from the user in rotations per minute. The design and curve of the foot pedal, as well as the stability of the cooler, aid in the optimization of input RPM and prevention of user fatigue for the required centrifugation duration.
One of the main components of our design we don't want breaking while our centrifuge is running is the axle. As the axle has both the weight of the rotor and a torque applied on the other end, it has a high risk of failure if not designed properly. To determine if the axle would fail under the current loading conditions, a finite element analysis was completed in ANSYS. The calculated von Mies maximum stress of the axle was 0.3138 megapascals. This value is much less than the ultimate stress of the material at 460 megapascals. During this simulation, it was also determined that the factor of safety of the axle was 15. The values of both the maximum stress and the factor of safety prove that under our current loading conditions, the axle should not fail.
So now looking at how long we actually need to centrifuge for, some things that we need to consider are the relative centrifugal force and the RPM, which is the rotations per minute. And so we approximated about 2,000 RPM based on the 120 pumps per minute foot pedal, which was assumed. And so assuming an infinitely long tube and blood as a sphere, you can actually derive two equations, one for the volume of plasma and one for the fraction cleared. And so when we're looking at the fraction of blood that we need to clear, it needs to be about 50%. To actually diagnose anemia. And so looking at the two graphs, kind of the x-axis, you can see between 13 to 15% we can clear the required amount.
The standards for electric centrifuges that were used to guide the final design were provided by the American Laboratory, OSU Environmental Health and Safety, ISO International Standard 6178, IEC Standard 61010-2-020, and the FDA SOR 98-282. Certain regulations were omitted as they were not applicable to non-electrical devices. These standards were used to guide major aspects of the design. This included material selection, as necessary properties such as fatigue, corrosion, and abrasion resistance, as well as ductility, were required to be able to withstand the stress loads and environmental factors. The minimum required centrifugal force to achieve proper sedimentation also followed these regulations, as well as failure assessments and precautions, which led to the design having a solid casing with a locking lid. And finally, it also included the design having proper stability while in use, which was determined using the center of mass and the center of gravity.
And so looking at the overall impact of this non-electric centrifuge, the three main things, societal, environmental, and economic impacts. In terms of society, there's a huge education piece to this, empowering the community to learn about healthcare, learn about technology, and really providing them technology education. And this will improve job promotion and also just accessibility to the healthcare field, kind of as we know it. Looking at the environment, there's no need for infrastructure or destroying the land, which goes a long way in these very context-specific communities, especially in Indigenous communities. And then in terms of economic benefit, looking at reducing foreign aid and travel to these communities, especially in times like today, these communities need to be sustainable. So just kind of in conclusion and wrapping up this presentation, we designed a non-electric centrifuge to be used in rural and remote Amazonian communities. And so we went through the material selection, the design defense, kind of how we came up with this solution, and the overall impact and kind of what we're trying to do. And so I think the most important thing here is that we, as engineers, look to design technology for these context-specific communities, and really the communities that need it and using technology to benefit them. As much as technology is advancing and it's phenomenal, we can't leave behind people and we cannot make a larger gap in healthcare than there already is.